purpose of the speech is to have an overview on a research area. So I won't be technical, but if you have any questions, please feel free to ask. I hope the talk is accessible to everyone, even non-experts of this specific topic. Maybe one of the quintessential questions in computer science and computer engineering is how to extract information from a set of data. Typically, the information is constructed by relating the data. The data by themselves do not represent information. The information is constructed and computed by relating data. And a fundamental approach that many systems and methods use is to construct a structure of this data, a data structure, where the relations between the data is clear, and then you can process and extract the information from your data. For example, here you have this set of raw data, and you can construct a table. This is typical approach in relational databases. You construct one or more tables. Now, why am I saying so? Because I want to make an experiment with you guys. Now, the experiment is coming. Let's consider a case when you have two tables. So one table is railway stations. So you have an ID and the name of the station. So for example, 0 is Rome, 1 is Milan, 2 is Naples, 3 Florence, and so on. So the ID of the station corresponds to the name of the city where the station is. And then we have another table named connections from to. For example, the first tuple, the first row in the table says 0, 1. It means that there is the station of Rome, there is the station of Milan, and then you have a train track that goes from Rome to Milan. So you have a connection, direct connection. So connections describes a network, a railway network. Now comes the experiment. So suppose that the experiment is a human-centric experiment. So which means that you need to make a decision based on the data that you see. Now, the question is, you have to decide whether there is a station, a railway station, whose shutdown would disconnect the network. So which means that if the railway station is shut off, then there are some portions of your railway network that are disconnected from others. You cannot go from A to B because you had to pass through the shutdown railway station. And I show you the same table as before. I just split into two parts because of reasons of space. And let's say that efficiency matters in decision making. Let's say that you have 10 seconds. Time over. Have you made the decision? Probably not. Now let's try with a different representation of the same data set. This is the same data set where, around the circles you have the name of the stations, and then you have the connections between the nodes. And the same question, and half the time. Is there a station such that if you shut down the station, then a portion of the network is connecting from another? Half the time. Now I think that all of you figured it out, right? It's number 7. Okay, so this is a node link straight line visualization of the relational data set that we've seen before. Now, you may say, okay, so node link node link visualization is a good thing. Not always. Let's consider the same question, but a different visualization of the same data sets. In this visualization, it's very hard to understand that 7 is the critical cut vertex, as we say, technically speaking. So not only you need to choose, so what is the moral here? The moral of the story is that not only, depending on the application, you have to choose the more suitable representation paradigm for your data set, but also you have to find the algorithms that would represent the data in a readable way. Readable means that the representation must convey the information you're looking for. All right? Okay. So, and this readability is, I will talk about it later, but the readability is concerned with combinatorial optimization goals for algorithms. And I will come back to this later. So what is then graph drawing and network visualization? Graph drawing and network visualization is a field of computer science which considers the following problem. In input, you have a network that from an algebraic point of view is described by a structure called graph. So you have a set of vertices and a set of edges, connections that describe the relationships between your data. The data are the vertices. And then you want to design a system that I will call NetVis system here, that produces as output a visualization of your data and of your relationship, which makes it easy to extract the information you're interested in. Of course, to do so, you need some additional criteria that are the readability requirements and the visualization metaphor. So if you think about this area and you think about what you need, what knowledge you need to construct, design and realize such systems, then you will easily see that the area is an intersection of three areas of computer science. One is human-computer interaction, because the end user will need to interact with the representation that you offer in many different ways. The representation is not static, but you interact, you ask queries, and then the system would give you back new representation, and so on and so forth. Then, as I said, I mean, you have to compute efficiently and effectively representations that are accurate for the query and the application that you have, that you are considering. And so there is complexity theory and algorithm design. And the third component is engineering of the algorithms that you've designed and user studies that should either confirm what you've done or maybe propose new aesthetics and new requirements on which you should optimize. So in the this is to say that it was kind of a prologue. I mean, we now in the rest, I will try and cover a little bit of these three components and explain how they relate to this area. So I will talk about graph visualization metaphors and interaction paradigms, and this is the human-computer interaction side of the area. I will briefly talk about three famous algorithmic frameworks, and this is the algorithmic part. And then I will talk about approaches to define readability requirements, which is the user studies. And finally, conclude with some future research directions. If you have any questions during the talk, please interrupt me. I'll be happy to answer. All right, so let's start with the visualization metaphors. Most of my talk will be about the node-link metaphor, but before going into that, I wish to mention at least some other widely used metaphors. Already between the node-link metaphors, there are different variants. You can have a straight line, which you already saw, or we can have a node-link orthogonal, that is particularly common in software engineering or information systems design, where the edges are polylines of horizontal and vertical segments, and whenever two such segments meet, you have what's called technically a bend along the edge. Or you can have the matrix, adjacency matrix representation. All of you must be aware of this type of representation for a graph, and I will get back to this later. But before, I want to also mention the space filling metaphor. Space filling metaphor is represents the vertices as rectangles, and the edges are represented by the inclusions of rectangles. For example, here you have on the left-hand side, you have a tree, and whose root is C, and then you have the rectangle representing C. Let me show you this. Just a sec. Okay, so here you have this node C, and this is the rectangle representing C. Then you have the children of C, pictures and music, are two rectangles that are inside the rectangle of C. The inclusion represents the edge, okay? Then you have ocean and desert, which are inside pictures, and song, which is inside music, which again represents the edges. Right? Related metaphor is this is a space filling metaphor. It's commonly used in the operating system environments, for example, to represent the structure of the memory structure in a hard disk. Linux uses it in its kernel. Another type of related representation is the contact representation. The contact representation, similar to the previous one, the vertices are regions, and the size of the region typically corresponds to the weight of the vertex. So here, this is a contact representation of the distribution of the population in the world in 1500. Then you can animate and see what happens in 1900, and then what happens in 1960, and what is the projection for 2050. Okay, so this is this type. Again, when regions touch, you have an edge. Here, the edges correspond to commercial exchanges, for example, or boundaries, simply geographic boundaries. Okay, now let me go with the interactions. How do you interact with these visualizations? Especially, we'll talk about the node link metaphor, although we shall also consider some other hybrid metaphors I will introduce later. So there are different ways of interacting with the final output of this network system. Different ways. We can classify them as full view, top-down, incremental, narrative, or multi-view. I will briefly discuss each of them. Let's start. Give me a sec. I want to go back to my original thing. Well, that's not. Okay, fine. Okay, so in the full view interaction, the user sees all data at once. So you have a system which computes a drawing, a representation, a layout of your network, and you see the whole network in front of you. Now, the pros are that all data are there. The cons are that if the data are too many, then it's difficult to explore. But if the network is small, like you see in a metro map, then the algorithms that compute metro maps representations, they have a full view approach. But if you have a much bigger graph, then it's hard to answer specific queries. You know, what happens to my specific node? What are its neighbors? If I take these two nodes, is there any relationship between these two nodes? That's very difficult to answer. Ben Schneiderman, in a pioneering and seminal paper in this field, said that the right approach is overview first, then zoom and filter for the full view. And I want to show you a little movie that I saw. This movie is by a system, a very popular system for the analysis of social networks. The name of the system is called Gephi. And here is the representation. See, here you have a full view. Now you're zooming in, looking for details. Now you go for a detail, very complicated detail, and now you filter out. It's filtering out and finding only a subnetwork. In a second you will see. Zooming some more, and now you have the wanted subnetwork. See, this is the approach. However, another interaction. The idea is to see the network at different levels of abstraction, which means that you can take very dense portions of your network and cluster them together So to find some kind of a skeleton of the network, and then you start the navigation by that skeleton and visit the details with a drill-in approach. For example, in this very small graph, I can take these portions, cluster them into big big nodes that hide subnetworks, and then I can explore them, right? And the representation paradigm metaphor that you can use for the exterior can be different from what you use in the interior. And this, in fact, suggested back in 2007 so-called hybrid visualization. In a hybrid visualization, this is a large authorship network. In a hybrid visualization, you have that these rectangles here are clusters of co-authors. And then when you expand the cluster, you can have a different metaphor. You can see that outside I'm using an orthogonal paradigm. Inside these edges are straight line segments, and then here I have an adjacency matrix. If the cluster is smaller, as it is here, then I can use again some straight line node link representation. This was first introduced by a group of French researchers in 2007, and since then, this type of representation, which is often called node tricks, has been extensively studied in the last 15 years. I want to show you another little movie of a recent development where you have these clusters, and here you see, what you see is now is a chord link representation of the cluster. So the outside, the chords of the circle are the nodes, and the chords, the arcs of the circle are the nodes, and the chords inside are the edges. And then here you have a matrix representation. Actually, this is let's see if I can stop it. No, I cannot. Well, that matrix representation, we'll see that the diagonal is not in the right place. I mean, it's a so-called row column independent matrix representation. And we scramble the rows and the columns so to reduce the number of crossings outside. And then you have another representation, which is the traditional matrix, adjacency matrix representation. So different types of representations. And then you can ask yourself, which one is better? Should I always use chord link? Should I always use the row column independent node tricks representation? Should I use the classical node tricks representation? Maybe the node link where I encircle my clusters with colors. And of course, you can then run tests. And I will get back to tests and how these tests are run later. But then this is ongoing work. Opposite to the top-down is the bottom-up, which is particularly suited for those applications that require some detective activities, investigation. So you start from a suspicious element in your data set. If you're looking for a virus, an infected piece of software, and then from there you want to see what are the neighbors, what are the pieces that are connected. So this is incremental. It's bottom up instead of top down. So you don't start from generic skeleton, but you start from a particular element. And this incremental interaction, we have used it in an interesting application, I believe, in cooperation with the Italian Revenue Agency and the financial police for contrasting tax evasion and money laundering in Italy. And nowadays we are my group is consulting the European Commission that wants to scale this technology to other countries. It's currently used by the Italian Revenue Agency, the technology I'm about to describe. And to do so, I will make a short detour in financial crimes for those who are interested. Financial crime, it's a worldwide critical problem, and often the way you do money laundering or strange patterns of relationships within elements. Maybe you make some transaction to a fake society, or a bank transfer to an old guy who has a very low pension, and you give all these people not much money, and they all go together to put this money in your bank account. There are different ways. You imagine that every year there is a congress about the new ways adopted by the criminals that have been invented by the criminals for money laundering and tax evasion. And in Italy in particular, this is a particular relevant problem. In the last years, more than 100 billion euros is with tax evasion. And what do the Italian Revenue Agency, called Agenzia delle Entrate, does with the financial police? They collect large amounts of data in different ways from different sources, documents, information on the web, and so on and so forth. And then they process this data. That is, they understand what they represent and the relationships between the data. And then once the processing has been done, so you have persons, companies, banks, bank accounts, transactions, so on, then you start analyzing. And when you start analyzing, the classical approach till about 5-6 years ago was to look at big tables. Excel files was the typical approach. And this is common not only in Italy, but in many other European countries. Now, what we did was, the observation I made at the beginning. Why don't you construct a social network? So the nodes can be the different actors. They could be physical people, or they could be companies, banks. And then the edges carry different semantics. They can be transactions, legal acts, friendship. There can be different ways of interaction between these nodes. And then once you have represented your data set with, say, a graph database, maybe you can use Neo4j or other technology you like. Then once you have that, then the detective, what she can do is to think about some critical patterns that she finds dangerous for some critical node, a node that she thinks can be dangerous. And then the system will return you either the pattern or the node, and from there you can explore. Let me show you the exploration. Here is the different types of attributes that can be given to the nodes or to the edges. And let me show you this incremental approach. Here, my detective asks for a specific pattern. This is one pattern you start with, and then you want to explore. Here you ask for a node, and then you see the neighbors, then you see the other neighbors, and you keep going like that. And at the end, if the detective decides that the pattern is critical and it may correspond to some illegal act, he would pass it to the financial police. Okay, and then you can study things like efficiency and accuracy, and we made such studies, and both accuracy and efficiencies have incremented significantly with this tool. The concept of the incremental interaction is, however, that you do not know the boundary of the network you're dealing with. So if this is another application used by RIPE. RIPE is the European agency that controls the traffic over internet. This is RIPE at the level of the autonomous systems. So this is the internet at the level of autonomous systems, and these are the relationships between the autonomous systems. And then you can see, if I do incremental construction here, that after only one click, I get a very complicated network. Okay, so this is the concept of the incremental interaction. So, this creates problems depending on the applications. Very recently, last year, there were some new ideas about how to interact with a large graph. And the new idea that is very recent, as I said, and still a very hot topic of study, is narrative interaction. Suppose that you have a very large network and you want to interact with the network, but if you look at it all together, it's too complex. And if you do some incremental, after a while, your screen is full of edges and nodes, and you do not know where to go. So then let's try something different, which is let us make a movie out of the graph. So let's visualize the graph, in other words, in a dynamic manner, such that a vertex appears in my movie for a while until all its neighbors have been realized, have been drawn, and then it disappears. So it gives me the time to analyze what that vertex does, and then it goes away. Okay? So that's the story that you want to make. For this is a small example, a toy example. So you have this network on the left, and the blackboard is where I want to draw my story. I start with the vertex. The green one stays there. The blue one goes there. Then I took the bluish, whatever, violet. Then when I get the violet, there is an edge to the blue. Keep going like that. And during the representation, you maintain something. So for example, you maintain that the edges that you see do not cross. All right, so you add your vertices in such a way that at any instant during the movie, your graph looks as if it were planar. Planar, technically speaking, means that it can be drawn without edge crossings. All right, this is what planar means generally. So you can do this. See that now has disappeared. A few vertices have disappeared because all their neighbors have been represented, and then you keep going. So you construct a movie. Of course, what's important is that those vertices that are acting in the current scene don't move from the scene to the next, because if they move all around, you lose what's called the mental map. So when you have to design and construct such a story that it's called the story plan, you have basically to find a total order on your set of vertices so that they appear in that order, and each of them has what's called a lifetime, and you have to design the lifetime so that some optimization readability criteria are satisfied. Okay, so it's a multi-objective combinatorial problem, optimization problem. Finally, and then we go to algorithms, the multi-view interaction. So you can say, hey, you told me about the different ways, but I would like to see all of them today. I would like to see the metric, the adjacency metrics represented. I would like to see the node links represented. I would like to see other charts. I would like to visualize my data in many different ways. And so this is, in fact, can be done. It offers many points of view, but the different views may introduce visual complexity, and so they are typically for advanced users. So this is an example I took from a recent paper with some friends in the Technische Universität of Wien, where we constructed this system to visualize the information diffusion in a network. Information diffusion means that you have a large network, you plant some seeds, they can correspond to viruses, they can be infection, or they can be good news, or they can be political influence. And then you want to understand what are the best positions for the seeds, so to influence your network, your actors as fast as possible. And here you have different visualizations of the phenomenon. For reasons of time, I'm skipping, I have the movie for this, but I'm skipping details. If you're interested, I'd be very happy to tell you more about this. But it gives you the idea that you can have multi-view for more advanced skills. Here, the users are algorithm engineers who want to simulate the planting of the seeds in different nodes of your network and see what happens. Okay? Okay, then let me skip this. And then let me go to the second part, the second big area of graph drawing and network visualization, which is algorithm design. You must have already gotten the idea that there are several optimization combinatorial problems behind these technologies. but I want to at least mention 3 famous algorithmic frameworks that are widely adopted. One is the so-called force-directed framework. So how to draw a graph? The idea of this framework is simple. It goes back to 1961. A Canadian mathematician named Tate, he wrote a paper, How to Draw a Graph, and there were the initial ideas. Then Peter Eads, that is a colleague from the University of Sydney, took these ideas and exploited them in many directions. But intuitively, it works as follows. You have your network. Every node, say, is a disk of metal. And every edge, say, is a spring. Then you also charge your disk of metal with a positive electrical charge so that they would repel one another. Then you take this thing and throw it in the air. Then when it goes down on the floor, it would look for a minimum of energy, right? I mean, the disks would try and repel each other, and the springs would like to attract the endpoints to each other. Now, the minimum of energy is the drawing, okay? So when we saw the representation in the incremental view, or when we saw the representation in Gephi, in those 2 little movies, those drawings were computed with this technology, force-directed. It is very easy to implement, and it's very popular in the market, very common. The drawback that it has is that the minimum of energy is found by solving iteratively differential equations. So then you have to use some numerical analysis tools, and this is at the expenses of efficiency and therefore scalability of the technology. So another famous algorithmic framework is so-called the Sugiyama's framework. Sugiyama, he was a researcher in Japan, and he came up with his students, Sugiyama, Takao, and Toda were the students, with this approach to showing the hierarchical structure of directed graphs. So if you have a directed graph, you want to show the vertices that come before, then the other vertices that are below, and so on and so forth. So the first thing, it is 4 steps. At each step, you consider a different optimization criteria. So the first step is to make your graph acyclic. That is, you don't have cyclic directed cycles. And this is done in this step. You want to minimize the number of edges that you are whose direction you invert. Here we have 1 edge. The second step is to assign the vertices to levels. And here you want not to use not too many levels, so to make the height of your drawing not too big, not too large. Then you have you permute the vertices on each level, so to reduce the number of crossings. And finally, you assign the final coordinates. Okay, so at each step you have a different optimization goal. You assign the coordinates, so to remove as much as possible the bends along the edges. The third framework is called topology shade metrics, and is typical in those systems that are common in software engineering, because they use orthogonal drawings, and also in the LSI. So here you start with a graph, and the first step is you planarize it. What planarize mean? What does planarize mean? Graphs often cannot be drawn with oh, time is over? No, I still have some time. Sorry. So most graphs cannot be drawn avoiding edge crossings. This is kind of bad news, but there is a famous theorem by Kuratowski that says that graphs are planar if they're sparse. They can have, actually, it's Euler first. Euler says that they must have at most 3n minus 6 edges. So while in general, the real graphs have super linear number of edges in general. So your graph may not be planar. And if the graph is non-planar, the planarization step introduces dummy vertices in the place of the crossings. And so in the planarization step, you want to insert as few dummy vertices as possible, because at the end you would remove the dummy vertices and you would get the crossing in your graph. Then, given a planar graph, you construct a shape of the drawing. That is orthogonalization step. Here you define the shape, and in this step, you want to minimize the number of bends. This is done in a beautiful way, the classical way, but there are new ones now, that is modeling the problem as a network flow problem, minimum cost network flow problem. And then you have the compaction. Compaction means construct a representation that has that occupies as little area as possible. Now, as I said, the force-directed approaches have the pros that are very popular, very easy to implement. The cons are that are typically suboptimal with respect to different readability requirements. So the optimization goals, they are heuristics, basically. So any heuristic would not give you the optimum or may not give you the optimum. If the optimum exists, it's possible to compute in polynomial time, and they are typically computationally demanding. So they suffer of scalability. The other two frameworks are much more accurate as when it comes to optimization of specific criteria. However, they suffer of some rigidity, because at any step, you optimize one criterion, and then this criterion cannot be changed by the next step. I two more slides about these two ideas. For the scalability of the force-directed, one approach that has been studied and is still studied is the one of the so-called multi-scale. Multi-scale means that you're coarsening your network, identifying a sparser subnetwork. You draw the sparser subnetwork, and once you've drawn the sparser subnetwork efficiently, you attach the vertices that are in the next level, in the next coarsening, in the less coarse level of your network to the drawing that you already have, and keep going like that. As for the rigidity, I want to give you an example to explain it. Suppose that, let's think about the topology chain matrix, and suppose that after planarization you get this drawing, this embedding. It's not a drawing, it's a planar embedding, so it gives you the cyclic order of the edges around the vertices. And now, given this, you construct this drawing, which respects the planar embedding that you've chosen. Now, the same graph, and suppose that at the end of the planarization I had this different planar embedding, then I would get this drawing of the same graph. Now, if you compare the two, see that the first one has linearly many bends. It's the minimum number of bends you can achieve with that given embedding. But in the second one, you have 0 bends. So the optimal solution with respect in the fixed embedding can be as bad as linear, so as bad as the size of your input compared with the optimal in the so-called variable embedding. And so, of course, at this point, the algorithmicians would start studying the complexity of the problem and heuristics, and of course, the problem it's a polynomial time solvable if the embedding is fixed, is NP-complete if the embedding is variable. I don't want to be technical here, but then you can study fixed parameter tractable approaches. You know, there is a whole literature about this. And I'd be happy to discuss some more, but I would like to conclude with this last part, that is how to define the aesthetics, what are the approaches to define the aesthetics in this area, and so the user studies a little bit, and then some future research directions. Do I have time? I think so, right? Yes, I still have a few minutes. Okay, so readability. How do we define what readable means? So the classical approach, which started in the mid-80s, is what I call the researcher-centric model. So in the researcher-centric model, there are researchers that have intuition about what a nice drawing should be. Based on this intuition, they translate this into optimization parameters called aesthetics, And these optimization parameters are translated into combinatorial optimization problems. Once you have the combinatorial optimization problem, then you design the algorithm, study complexity, design the algorithm, and then you code and run experiments and do ex post validations of the original intuition, which can go back to new studies about complexity or new intuitions. A typical example is edge crossing. Edge crossing, I already told you that you want to minimize the number of edge crossings in several moments of my talk. And in fact, the early researchers in the 80s who started basically the field, Sugiyama, Warshol, North, Battini, they had this intuition that crossings would affect the readability. So if you have a drawing of a network with many edges that cross each other, it's harder to read compared with the same network with fewer crossings. So the optimization goal is now minimize the number of edge crossings, and the algorithmic study started. So NP hardness, heuristics, fixed parameter approaches, and so on and so forth. And then user studies. Let me tell you some more about user studies, as I promised to. So the user study, the approach, typical approach is this. You hire a group of students, form a group of users, but they're typically they're students. And then you expose your users to drawings of graphs, to different drawings of the same graphs. So here is a drawing with more crossings. Here is the same graph with fewer crossings. And then you assign your students some tasks. For example, I highlight in both drawings a pair of vertices here, the same pair of vertices there, and I ask you, can you find a path? Is there a path? Is there a path? And then you measure time and error. And based on this, you derive some statistically significant conclusion by doing in-betweenness. There are different ways, of course, of running these experiments. Pioneering study by Helen Purchase in 1997 that showed with this type of studies that actually crossings are in fact worse than bands and then symmetries in the readability of a representative. So in fact, the crossings are really bad. But let me tell you a different approach and go back to crossings now. This second approach is called what I call a user-centric model. In the user-centric model, you start with the experiments. So you start to understand and speculate, how do people read graphs? How do people read the networks? And based on these human experiments, you develop theories on how people can read them. And based on the theories, you find the optimization criteria, and so the algorithm design, and finally the algorithm engineering part. And pioneering study in this user-centric model is by Peter Eads and this group in Sydney, Huang, Heath, and Hong, who in 2007, if I remember correctly, started a series of experiments using an eye tracker. So they were showing huge graphs on a wall, on a screen wall, very large, and then they were with the eye tracker. They were giving tasks, and they understood two things. One is, if you are given two nodes in a network and you ask whether there is a path between these two nodes, the human eye follows the so-called geodesic path tendency. So the first thing you do is you look for the straight line edge segment connecting the two nodes in space. We do it naturally. So if your path is very far from this geodesic connection, then it's harder to read. The second conclusion was that crossings are bad. Sometimes they are unavoidable. But if the crossings form 90-degree angles or big angles, so they're not very sharp, they do not affect as much the human eye and the human brain, as much as they do when they are very sharp. So based on these conclusions, for example, this is the work they did published in 2014. Then back in 2011, Peter Eads was in sabbatical in my lab in Perugia. We developed this idea to study drawings of networks where the crossings were allowed, but the crossings could only form 90-degree angles. They are called RAC drawings, right-angle crossing drawings. And since then, many studies have been published on the topic. This is called graph drawing beyond planarity as an area. People gave it even a name. And here it is a comparison of a drawing to the left where you have sharp crossing angles, and to the right you have large crossing angles. Okay, now the conclusion, some future research directions. One direction that I find particularly interesting is to further explore this user-centric model, to define new sets of aesthetics for graphs that require crossings in their drawings. For example, are there new aesthetics other than the crossing angle resolution, the geodesic path tendency? And here I have a second little experiment for you guys. Look at these two visualizations of two networks and tell me which one you find more readable, A or B? A. You find A more readable than B. Yeah, I was in another room. I was sitting there, and the experiment, I said A also. A is better than B. However, B has the minimum number of crossings, 24. A has 34 crossings, 10 more. And you know why you find it more readable? The reason is that in A, there are only a few edges that collect these crossings. If you remove 4 edges, the underlying structure does not have any crossings anymore. So the crossing minimization is not necessarily the thing you should be looking for. Maybe you should try and optimize the skewness, which is the number of edges whose removal makes your drawing planar. Okay. Then it's a second research direction, which is I told you about different approaches to interact with the visualization. In particular, the incremental and the story plan seem to try and solve the same application, respond to the same application requests. So it would be interesting to run user studies, perform user studies to compare them. The third interesting research direction is how to exploit these new technologies that are becoming cheap and accurate and very much available of virtual reality. So what does it mean, and when do you need to go into some virtual reality environment to visualize networks? And what are the optimization? What are the credibility criteria there? What are the optimization goals? What are the algorithmic challenges? This is a very, how can I say, fertile and yet unexplored field. Finally, what I consider the quantum jump. So, indeed, visualization has to do with us, but the way the human mind processes data is much more complex. You use sound, use tactile, use the possibility of touching. So what about considering a different approach to networks where you have a multimodal interaction with the networks? I wish to conclude with a quote by Donald Knuth. Donald Knuth is the winner of the Turing Award, which is the Nobel of computer science. He's an emeritus professor at Stanford, and he said the graph drawing is the best. He gave a speech. I was at the speech, and he wrote this: graph drawing is the best possible field I can think of. It merges aesthetics, mathematical beauty, and wonderful algorithms. It therefore provides a harmonic balance between the left and right brain parts. Thank you very much.
Thank you, Beppe, for the very, very nice talk, very inspiring. I guess behind such technologies, such ideas. A lot of the technologies are nowadays developed and depends on it. So really basic concept. Any question from the audience, please? Forse sarebbe. Okay, thank you for a very nice presentation. I have a couple more questions. The first one is about the importance of how you represent the same graph. It means that you have the same graph, same nodes, and same links, and you try to represent put down it in different ways. And there are some of them which are best for the understanding of the graph. How can this stuff, this kind of property that I don't know if it has a name, but this kind of property, how can be translated in terms of data structures to feed neural networks?
Okay. Okay.
Because it's the same graph, but like you put a different perspective.
Yeah, nice. Thank you. It's an interesting question. So, in the first place, you identify the requirements you want to have. So, how to draw your graph by considering the tasks, the users, and the data. So, it's kind of a triangle. This is called the triangle. Sylvia Mitch in Wien had this triangle, and then you may ask yourself, how can I use some neural network approaches to construct such drawings? There are at least two ways that I know. One is for the force-directed methods. As I said, when you study force-directed, you try and optimize some criteria. And so these criteria can be modeled as forces in your representation. And then you want to do some gradient descent to find the minimum. And the gradient descent can be implemented with using machine learning technologies. This is from a technical point of view, if you want, to represent your graph. Another completely different approach is to instead consider different weights. Suppose that, okay, I go back one step. Suppose that you express your optimization goal as a polynomial, where you have the different aesthetic criteria you can think of, for example, crossings, distance between any two vertices, and so on. And then you compute a polynomial with coefficients that are the weight, the importance that you want to give at that particular thing. So it's a summation of it's a polynomial, right? It's just a sum. And then you can train a machine on a family of graphs to understand what is the best weight to give in a specific application context to get the best drawing. So if you do some learning, which can also be deep learning in a sense, you can construct a machine that provides the best drawing in the given application. Let me say, though, that these techniques are known for the force-directed methods, which, as I said, are very popular, but do not optimize to the end your representation. So it really depends on what applications you're interested in. If you're interested in social network analysis, they are fine, because more or less, a picture is, if it's good and it can be slightly changed. But if you're interested, for example, in the LSI application, when the area is really important, then at the moment, neural networks aren't used yet.
Thank you. Second question, the last one. Your voice. Okay. When he was talking at a certain point of a way of a method which is based on, you mentioned right now too, on forces and repulsion and attraction. No? And he was telling us that it was a very straightforward way to find the minima. I'm wondering, what about a huge graph? Because I know this is very similar to minimization of complex molecules, where you have, but by the way, in chemistry, it's graph theory applied to atoms, in a sense.
Yes.
So
Yeah, good point.
it is all but easy to find the global minimum, and sub-question, different minima, they have a meaning?
Yeah, good, very good questions indeed. So as I said, these techniques suffer of scalability. So if the graph is large, then you have to do this coarsening, for example. But when the graph is very large, then you can try distributed approaches. So the typical approach is, or not typical, the approach we try in my lab is the so-called think like a vertex approach. So instead of having some global optimization, which, as you say, can bring you to a local minimum, not to the global minimum, you can, for example, use simulated annealing, bring you to some local minimum, not the global. You can consider a different point of view. So you think like a vertex. So the vertex tells its neighbors what is its current position, and he knows the forces to only just its neighbors, and it doesn't know the rest of the network. Just know its neighbors, and then you try and compute a drawing based on this local information. This think like a vertex works in a distributed environment. Of course, it's much faster. Sometimes the drawings are a little worse because it doesn't look at the global optimization problem, but just the local.
Thank you.
So, thanks. Nice questions. Thank you.
Are there other questions? Okay. So thank you again.
We're on time. Ok, grazie.
Grazie.